We know now how to design the joint for tomorrow. But what about its behavior in 10 years or 20 years? What about the effect of water, temperature, fatigue, the loading type? These topics will be discussed in the last module, module 12, durability. So now we know how to design our joint, but we know how to design for tomorrow. We don't know how to design in the long term, taking into account effects such as the water, temperature, or the loading type such as fatigue, creep. That's what we are going to see now. This is a very, very important issue. It's the durability. So let's start with the hygrothermal aging effects. Adhesives are polymers, and polymers absorb water. The water can diffuse inside the adhesive, and it can fill basically gaps, and there are lots of gaps between the molecules, or combine with the molecules. It's called bound water. But what we want to know is how fast the water ingresses, diffuses into the polymer. This can be done by weighing small samples of the adhesive from time to time periodically. And if we represent the results in a graph, weight gain versus square root of time, we get this type of curve. And with this curve, we can determine the coefficient of diffusion of the material. It's important to know how fast the water goes in, but it's also important to know how the water affects the stress-strain curve. Then we need to do dog bone or to take dog bone specimens, tensile load them, and see how is the stress-strain curve. You have here the results, stress, strain. This is the virgin material without any water. As you increase the amount of water in the adhesive, the strength goes down and the ductility goes up. But be careful, if you exaggerate, you might have chemical degradation of the adhesive caused by hydrolysis when the water breaks the molecules of the polymer. In that case, you cannot go back here by drying the adhesive. Here, if you dry, you can go back. It's called physical degradation. When you have chemical degradation, it's over. You cannot recover the adhesive. So a bit of water, it's not bad actually, because it increases the ductility, and we know that the ductility is very good for the joint strength. We have seen that in the joint design part. Okay, the temperature we know, we have discussed that previously. When we go at subsonic speed, we have very low temperature, but if we go at supersonic speeds, for example, Mach 2 in Concorde, we can reach this temperature. So it's important to determine the adhesive properties when you have temperature fluctuations. And we know that as the temperature increases, the strength decreases and the ductility increases. Again, a bit of temperature is not bad because we get a higher ductility. But be careful, we cannot go above the Tg because then we lose completely the strength. So that's for the environmental factors. What about the loading conditions? And starting with the most important one, which is fatigue. Fatigue is probably the most important loading condition when we design an aircraft. And fatigue basically is caused by the pressurization of the aircraft, which is done every time you fly. One flight is equal to one cycle. That's because we fly at very high altitude, and we need to put pressure inside so that we have a pressure more or less equal to the pressure that exists at 7,000 feet, which is a breathable situation. So this pressure will cause in the joints that are here, that can be rivets and adhesives, they cause tensile loading in these joints. The loading can be more or less irregular, but in the laboratory we will apply a perfectly regular type of load. You have here all the nomenclature, the definition for the stress components associated to this stress wave. That's not the most important. The most important is to understand which approaches we have to design in terms of fatigue. And the first approach is the total fatigue SN approach. you have a SN curve where you have the stress applied as a function of the number of cycles. Typically you have something like that. You apply this in a joint that is close to the real joint, and you know for a particular stress how many cycles the joint withstand. In this slide you have something a bit more complicated, because in fact this SN curve can vary a lot as a function of the geometry and the loading mode, if it's mode 1, if it's more mode 2. So we have recently been looking at this, and we have generated different types of SN curves as a function of geometry, and we collapsed these SN curves in one using an effective stress, a stress component that takes into account several types of stress. And this allows us to have one only curve that takes into account these factors, the geometry and the mode mixity. Then in practice what you need to do is a finite element analysis of your aircraft, and for a particular effective stress then you can determine the number of cycles to failure. Of course this will depend on temperature and humidity level, so if you want to take these into account you need to generate also SN curves for these conditions. So that's the first approach, the total fatigue approach, the SN approach. The other approach is the crack growth approach. This approach assumes that the aircraft has cracks, and it will try to calculate how fast the crack grows in one cycle. But for this you need to generate the Paris law of the adhesive.
When a joint is subjected to fluctuating stresses, like this one, it will experience a specific type of damage which is known as fatigue. So it's very important to characterize adhesive joints in terms of fatigue, specifically in terms of fatigue crack propagation. In this DCB test, we apply a cyclic loading to the joint, and we analyze the rate of crack propagation. The crack propagates from a small size to a big size, and we analyze the rate of crack growth under cyclic loading conditions.
Again, the Paris law will change a lot with temperature, mode mixity, humidity level, so a lot of data need to be generated. Fatigue is really one of the main concerns when we talk about designing aircraft, and as you know, I told you that since the beginning, adhesives are used everywhere in the aircraft, but be careful, they are used only in secondary structures. That means structures that in case of failure they will not damage completely the aircraft, and the aircraft can actually still fly. They are not used alone in primary structures. If they are used in primary structures, then they are used with hybrid joints. That means you put the adhesive plus something else. You have here the plus something else. Imagine the fuselage, you have the stringers, you have the ribs. This in general is reinforced with a patch adhesively bonded. Then you have a hybrid joint, you have the rivets plus the adhesive. And this is in line with the fail-safe design approach that is used in aircraft, where in case one fails, you still have the other one. It's much safer, and this, in fact, is used in primary structures. Temperature, we have talked about that. If we talk about temperature, we need to talk also about creep. And this is especially important for the supersonic aircraft or for the noble aircraft with the joint close to the engine. So you need to generate the creep curve, strain versus time, and define the strain rate in the second stage and the time to failure. This, of course, varies a lot with the temperature, the applied stress, and the humidity level. So if you want to design taking into account all these factors, you need to generate an awful lot of data. So really, the durability is a very, very, very time-consuming subject, but you need to do it if you want to have a realistic failure load prediction in the long term. But again, we are talking about very, very complex issues, and in terms of research, that's probably the most important research topic in the world of adhesive bonding at the moment.
This concludes this series. We have 12 modules on adhesive bonding applied to aeronautical and aerospace applications, useful at the master level for people interested in aeronautics and aerospace. If you want to know a bit more, there is another series with 30 modules where adhesive bonding is described in more detail.